Welcome to Hot Chips 29. Session 6, Neural Net 1.
I'm happy to announce the start of the first of 2 neural network-focused sessions. So our first speaker is Dr. Chris Nicol. He's the CTO of Wave Computing and the lead architect of the DPU architecture. Prior to Wave, Chris was CTO of embedded systems at NICTA, an Australian R&D organization that he helped to establish. Prior to NICTA, Dr. Nicol founded Bell Labs Research in Australia and Agile Systems in Australia. He worked for Bell Labs in New Jersey, where he co-architected the first multiprocessor SoC. He has a PhD from the University of New South Wales and an MBA from the Australian School of Management. He is an inventor on 22 US patents.
Thank you. Thank you. So I'm going to go through these slides quite quickly so I can get to the technical stuff at the end. Wave Computing is a startup company, one of the rare startup companies that build silicon chips. It's very difficult to keep ourselves funded. I sympathized with the speaker yesterday from SciHive that said innovation in the semiconductor industry is incredibly difficult to get funded. We were founded in 2010. We're venture-backed. We're headquartered in Campbell, California. We have 53 people working with us, over 60 patents. We've invented a data flow processing unit that I will describe to you today, as well as the system that it goes into. The architecture is a coarse-grained reconfigurable array, which is very different probably to most of the architectures that you would be seeing presented here. You can think of it as a hybrid between an FPGA and a many-core. We statically schedule data flow graphs onto this massive array of processors. The chip that I present has 16,000 processors on it. And we're now accepting qualified customers for our early access program. The challenges of machine learning, I'm sure everyone here is familiar with these. Extended training times are problematic. It takes weeks to tune and then train typical deep neural nets. And the sizes of the problems and the sizes of the models, the sizes of the data centers, the data sets are growing. So it's a very interesting application for high compute. Hardware for accelerating machine learning was typically used, created for other applications. So people are using GPUs today but they were created for graphics. FPGAs are being used today, but they were really intended for RTL emulation. And we believe that there's more data actually coming in from the edge. For example, an autonomous vehicle per year will generate about 2 petabytes of data. So to take all of that data into the data center in order to process it and train it will actually be very difficult. So we expect to see that the training or the incremental training of neural nets is actually going to migrate from the data center out toward the edge. This just shows this chart. It's a chart that was presented by Google from their very first TensorFlow paper. And it's their EEG visualization of training Inception v3 on a CPU plus GPU system. In that system, I think they had multiple GPUs and multiple CPUs. And what this shows is the utilization of the threads on the GPUs and the CPUs. And those black arrows there are the threads on the CPUs, which show the critical path of the computation. And you can see that there's a lot of time there when the GPU is actually waiting on the CPU. Now, of course, cuDNN has gotten better, and TensorFlow has gotten better, and MixNet and other networks and so forth are actually better at scaling these systems. But this points to what I believe is a fundamental problem with today's definition of heterogeneous computing. And today's definition of heterogeneous computing basically says that the master or the control runs on the CPU, and the accelerator is kind of dumb. This means your runtime API runs on the CPU, and the slave has to wait for the CPU to tell it what to do. And we want to get away from that. So the approach that we use is called Dataflow computing, and we have designed a chip and a computer that uses that chip for executing Dataflow graphs. Dataflow graphs are used everywhere in deep learning. In fact, the flow in TensorFlow is Dataflow computing. You take a model like this on a network like, say, Inception or any of these networks, and the workflow generates a Dataflow graph that you then have to execute. If you execute that Dataflow graph, it will train that network. So what we do is we actually, at runtime, take that Dataflow graph from the workflow like TensorFlow Cafe, and we convert that at runtime directly into a Dataflow graph that executes without a CPU. And we map that into our Dataflow computing chips. This is the chip that we have created. It's in 16 FinFET. It has 16,000 processors plus 8,000 arithmetic co-processors. It's completely self-timed. It has 181 peak teraops per second. Those are 8-bit operations. It can do 8-bit, 16-bit, 24-bit, 32-bit, up to 64-bit, and it can change that type of precision that it's working with cycle by cycle. Those 16,000 processors work at an average execution rate of 6.7 gigahertz. So 16,000 processors, 6.7 gigahertz. That's over 200 square millimeters. Distributing a clock at that rate is not investable. It's not possible because of jitter. The clock jitter is actually greater than the clock period. So that is actually the reason we used a globally asynchronous, locally synchronous timing synchronization mechanism. It has 4 HMC cube interfaces for high-speed memory. And it also has 2 DDR4 interfaces for high-capacity memory. It has a PCIe Gen 3 16-lane interface for connecting to a host. But remember, the runtime API, there is no runtime API running on that host. So this shows 4 of these chips on a board. And this slide shows why we use HMC. HMC is actually a multi-port memory, and you can cascade those cubes. Another reason we used HMC was we just didn't want to incur all of the challenges associated with 2.5D integration for a small startup. But you can see here that the DPUs actually have a lot of interconnectivity through those HMC cubes. Now, if you're executing a Dataflow graph, most of the communication is local from node to node in that graph. Now, there are issues about, we use a mechanism called slack matching in order to balance the delays through the execution of that Dataflow graph. The way to do that is to insert FIFO buffers between your nodes. By injecting latency, you can balance the throughput through that graph and increase the effective utilization and the throughput. Now, we implement these FIFOs that are storing tensors between the DPUs in these HMC cubes, which means we actually don't have a lot of data networking bandwidth between those DPU chips. Most of the data flows through those HMC cubes. And we put 4 of these boards into a box and put the box into a rack. And there's no CPU in that box. We can stack those boxes and create a scale-up node with 1 million processors in it. And we still have to put a runtime server. We put a server there where we run a session manager, and that session manager interfaces to the workflow like TensorFlow. In fact, we can even take keras. We can take raw keras in. And yes, we actually have the mechanisms in our Dataflow graph computations to compute the gradients. I'm going to get into the architecture of the chip now. It's a coarse-grained reconfigurable array. It's really spatial computing. When you take a program and compile it to a many-processor core, you still have to partition that program into threads that run on each of the processors. And this is the problem with putting 1,000 CPUs on a chip. You can put 1,000 DSPs or 1,000 CPUs on a chip. In fact, there's an example, a poster example outside. But how do you program them? And OpenCL is not an answer. So the way to what we do is we take a high-level language, we partition it into a Dataflow graph, and then our tools spatially compile and schedule and map and route software onto a tightly coupled, interconnected fabric of compute processors. So this shows the processing element itself, and you can see it's an accumulator machine. The output of the accumulator, you can see there is 2B, 2C, 2D. These are immediately available to my neighbors. And the inputs from my neighbors are immediately available as an operand in that arithmetic unit. What this means is that we designed it and architected it and floor planned it bottom up so that it was cheaper and faster to move data from one processor to a neighboring processor than it was to stick it in a register and reuse it in the local processor. By doing that, it's cheap and fast to keep data moving between the processors, which is the whole concept of Dataflow computing. We put 16 of these processors into what we call a cluster of processors, and we connect them up to large blocks of memory. Each of those processors has their own separate instruction memory. They're 8-bit processors. They can run at MIMD. They can be ganged together to do SIMD operations at 8, 16-bit, 32-bit, and so forth at runtime by the instructions, and they each can dispatch operands to co-processors that do arithmetic, like multiply, accumulate, sign, unsigned, multiply, accumulate operations with saturation. We also have barrel shifting and other bit processing and so forth in there. Now, this is a data-driven machine. I'm going to show in the next couple of slides, if there's no data for this machine to execute, it doesn't do anything. And it can gate its clocks and so forth. I mentioned the word clock, and I said it's self-timed. I'll explain that later. Then what we have is the ability to communicate between the processors using a switch fabric, which is itself instruction-driven and statically scheduled by the compiler. So our compiler takes a thread of code, like a high-level block of code, say in AES 256, or a matrix model, or a softmax operation. We take that, and we actually take that into a Dataflow graph and then just spray it out as a 3D block of instructions, being 2D in space on processors, and the third dimension is time in the instruction memory. And they communicate through these switches. We have word-level switches and byte-level switches. Everything in this machine is running at 6.7 gigahertz. And we can move data from processor to processor at 6.7 gigahertz. The bisection bandwidth of this machine is 6.8 terabytes per second in either vertical or horizontal direction. And that's for a 32 by 32 array of these clusters. These switches also support fan-in and fan-out. So it's very easy, again, for Dataflow computing to actually take an input and spread it out, because it's very important to do that. And the fan-in capability is also very important for if you have a large group of processors, one of them is going to generate a result, maybe based on the data that you're providing, but you don't know which one, you then need a fan-in capability into your Dataflow graph. This explains how the data-driven power management works on this chip. When there is nothing to do, the processors go to sleep. So the bottom left hand there, you can see on the left-hand side, the processors are all asleep, but the switch fabric keeps running. So it's still running and moving data through a static schedule through all of these processes. But when data arrives, that must be consumed or processed by that collection of processes, it wakes them up. So when the data arrives, it wakes them up, they do their processing, and then they execute a sleep instruction and put themselves back to sleep as the data flows out. Now, if you sustain a stream of data flowing through this, it will, of course, stay awake until the stream stops. Now, I mentioned before you've got a static schedule in the switch fabric that is controlled by the compiler, but the outside world is transaction-based. In the rest of the SoC, for example, it's all transaction-based using a network on chip like HC. In that case, we actually think of the internal world of our chip, even though there's no clock in it, we think of it as synchronous, and the outside world as asynchronous, because I can't tell when that data is going to come. There could be wait states and all sorts of other things in round-trip delays, and could be contention in that knock. So as the data comes in, we actually store it all through FIFOs, and we realign that data to the internal self-timed static schedule. And that's what happens in these DPU interfaces. We have 32 of these DPU interfaces around the edge of this processor fabric. Each one of them contains a master interface and a slave interface. The master interface can do about 96 outstanding transactions, so we can queue them up, and all of the data coming in is then streamed in through DMA to the destination memories. We then put a number of these, we call them compute machines, and we load them together and create this massive fabric. It's about 200 square millimeters. It's all full custom digital. The logic used inside them is something resembling self-timed domino with semi-static. And this shows the memory hierarchy. You've got those HC channels, 0 through 31, each one with a slave, so the host can be communicating with any of the tasks running in this machine at the same time as all of the tasks running in the machine are accessing external memory or accessing high bandwidth memory or the DDR memory, all at the same time. You have thousands of outstanding transactions running at once. In fact, this machine can support sustain 4 billion random access 16-byte transfers per second to HMC. Now I'm going to get into the synchronization mechanism. As I said before, you put 16,000 processors on a chip and 200 square millimeters. You cannot clock it at that rate because of the clock jitter. We actually have this circuitry included, the sync block. What happens is we don't do a full handshake with our neighbors. We send a signal, and when I receive the signal from my 4 neighbors and I know that I've completed my current instruction, I advance. That's how this mechanism works. The intent here is to align the edges between the locally generated clocks in neighboring processors. That enables us to communicate robustly with our neighbors. I can't communicate robustly with someone distant in the machine, so all of the communication in this fabric is local. Using this mechanism and the circuits inside this mechanism, we achieve very high accuracy or alignment of our clocks within 6 picoseconds at 140 picosecond cycle time. So because we have no global signal, we don't even have a reset. So resetting this machine is a challenge. What we do is we propagate from the bottom left to the top right, for example, a signal that propagates clock after clock throughout that fabric. And when that signal arrives, each of the processors will actually initiate a counter from a loaded, it loads an initial value into a counter based on its Manhattan distance from the end cluster, and it then counts up to 0. When they all reach 0, they're all at the same instruction, the same program counter. And this is really important for a statically scheduled machine. You have to keep all the program counters aligned. Now, we, at runtime, load programs in and out of this machine very quickly. The way we do that is we instruct, say for example, I wanted to remove the old kernel that's running in this machine. I program those old kernels, I send it a slow signal to say, when this propagate comes through, I'm going to place you into configuration mode. That signal then sweeps through, they stop, but all the other processes keep running. Now those processes have stopped, I can do high-speed DMA directly into their instruction memories. And again, remember, no global signal. All of this is done in a cellular manner. Then once the instructions are loaded into the instruction memories for those processes, I then sweep another propagate signal through. When it reaches, they all count down again, and then they're back in sync with all of their neighbors. This whole process takes a few microseconds. You can actually very quickly, at runtime, reload programs in and out of this machine. Now, when we have a compile flow, we take a high-level program and we compile it into a spatial block. Now, that block can actually be loaded anywhere in the machine at runtime. It's essentially virtually addressed. But we have a problem. Say on the left here, I've got kernel 1 and kernel 2 running in this processor fabric, and I want to load kernel 3. And notice that it's spatial here, right? So the IOs are at the bottom of kernel 3, and it's been spatially compiled previously by our compiler. So I want to load this into the machine. Well, the first thing I've got to do is figure out where to load it, and it's very different from an FPGA. This is not defined offline, this is defined online. When the chip's running, I look at where I'm going to load that program. And then I figure out, okay, I actually have to route to that program at runtime. And it looks like if I'm going to load it here in the top right, I've got to route the IOs through kernel 2. Our SDK, when it compiles a program, outputs what we call a parity map, which tells us all of the available switch instructions that can be used by the online router. So we load program 3 in. Now, because we're going to route through program 2, we have to actually stop it from executing, so we temporarily pause it. We blast instructions into its switches in order to connect the IOs to program 3, and then restart the whole thing with that propagate signal again. Dynamic reconfiguration, arbitrary, spatial computing, loading in and out of the machine. You can use, you can run OpenCL on this machine very easily. The average mount time is less than a millisecond, and that's usually for the computation of the paths. We use a runtime router called, uses the A-star routing algorithm for doing that. So this brings us to the software stack. We have 4 of these boxes. There's a million processors in those, a whole bunch of DDR and HMC memory. As I said before, we're actually in the machine learning is actually the memory business. It's not really the processing, it's the memory. And we have a server on top which runs our session manager. It receives the Dataflow graph from the workflow, like TensorFlow. It receives it at runtime, processes it. It then instantiates from our library. Think of it as our Dataflow equivalent of cuDNN. It instantiates a library. It stitches up a Dataflow graph, a static Dataflow graph, that is then capable of running autonomously across all of those boxes. And then once it's done, all it has to do is apply the data. You'll notice at the bottom here we have an offline flow, which is our SDK. We've been developing this compiler for 5-6 years, with over half of our funding has gone into the development of this compiler. And what it does is, I'm going to come back to that slide. What it does is it actually has an LLVM front end. So we take a high-level language like C, feed it through CLang, get LLVM. We then generate what we call a WaveFlow graph, which is a byte-level flow graph from any input language. We compile that and link it using a static linker, using a SAT solver, and we're publishing that at ICCAD later this year. This actually gives us better instruction utilization and efficiency than we can get using assembler programming on this machine by hand. Substantially better. We can simulate those byte-level flow graphs. We also have an architectural simulator which simulates all of the instruction-level communication. And we have a higher-level simulator which simulates data flow graphs executing across several chips. And this is how we generate our WaveFlow agents. Now notice, this is specifically for machine learning, because what I'm feeding in here is, say, GEM, softmax. You can actually feed any algorithm in there. So we've done AES-256 encryption, we've done LZRW3 compression, we've done FFTs, we've done LDPC, we've done turbo decoding, we've done Viterbo decoding, all of these, and benchmark them all against FPGAs, and we achieve about the same level of computational efficiency and area efficiency as an FPGA. And yet you've still got this dynamic runtime capability and the ability to compile from a high-level language. This shows a data flow graph representation in our byte-level flow graph format that is input to the tools, and what is shown there on the left is the sequence of instructions executing on the processors, multiple processors. This is for a sum of products. So it shows you the sort of density of instructions that we get executing in this machine. Now in our session manager, we take a high-level model like Inception v4. We've taken this from Keras. And it generates a data flow graph that we can then schedule and compile and map, across our processors. We allocate blocks of memory in the HMC cubes. These set up the FIFOs. We tune the sizes of the FIFOs in order to balance the computation and maximize the computational utilization of all of the arithmetics in the system. And we can scale that across chips in a board, boards in a box, and boxes across a node in the network. And this shows you the kind of performance that we get for training and inferencing neural network models using this approach. This is with 4 boxes of 64 DPUs. AlexNet were almost achieving 1 million images per second of inferencing, and we can train it in 40 minutes. We've also done sequence to sequence, which we train in 7 hours and 15 minutes. One of the reasons we do so well with that is because of our random access performance. So while everybody's benchmarking image processing, we can actually do a lot of natural language processing, because there you're doing lots of random access lookups into big tables, big dictionaries, and so forth, and our system can actually handle that very, very efficiently. As I said before, 4 billion random access operations per second, 16-byte transfers. And we're accepting customers into our early access program. Thank you.
David Cantor. So asynchronous logic is usually only helpful in getting rid of clock power. Can you talk about the operating voltage range that it allows you to achieve?
Okay, first, you said asynchronous logic. I never did. So we are globally asynchronous, locally synchronous. So we use a standard off-the-shelf tool flow for the compilation of our systems. That said, it is PVT robust, primarily because of that self-synchronization clock mechanism. It does not run down at the deep sub-threshold range. It's not like the Eta compute processor that we saw yesterday, mainly because we're using off-the-shelf memories that don't allow you to scale down to that level of voltage. But it's quite possible for this sort of system to actually run at varying voltages and to tune that voltage based on the amount of processing you have to do. Now, what you would typically do is you've got all those FIFOs all the way around the outside there that are communicating with the SoC, 32 AXI interconnect connections. You can monitor the amount of data in those FIFOs. As the data drains, you know that the machine's running too fast and you can increase them. decrease the voltage until they fill up. And as they fill up, you then increase. So you can use a simple mechanism like that for adjusting the voltage.
And when you described some of the logic, you used the terms something along the lines of self-resetting domino.
Yeah, some of the patents, I think, are already sort of, the disclosures are available. If you think of dynamic CVSL, CVSL logic, basically you have F and F bar, and you're pre-charging the two nodes, right? In that case, whether you're computing a logic 1 or computing a logic 0, you get an edge. That edge tells you exactly when that gate, whether it's computing 0 or 1, has evaluated. You can use that signal to feed back and actually regenerate your local clock. We had to convince our investors that this was actually a feasible approach, and we did a test chip in 2012, and it ran at 11 gigahertz in the lab using this approach. That clock that comes off the completion, it's a completion, but it's not computed in the way that people were talking about yesterday. But when you get that signal, you can then feed that straight back into your IRAMs.
Thank you.
Okay, I think we have we have time for just one more question over here.
Jack, NVIDIA. When you were showing the one of the problems with other accelerator architectures, you were showing how when new kernels need to be kind of loaded onto the GPU or accelerator, that you had to kind of synchronize and be controlled by the CPU. In your architecture, you talked about having to load new kernels and taking a millisecond to do so. Is it not done by a control CPU? Do you have your own sort of mechanism to do that? How do you manage that and do that more efficiently than other architectures swapping in and out kernels?
That is a good question. On one of my slides, you will notice there is an MCU in this chip. We use that MCU for actually moving stuff in and out, programs in and out of this chip at runtime. But the programs themselves determine when they're going to be moved in and out. No, there's no runtime API sitting on a host saying now swap in, now swap out. The programs themselves communicate with the MCU, and the MCU fast DMA transfers the programs in and out of the chip. It controls that propagate signal. We also have a program cache on chip so that we cache the programs in and out as we run them. So it's slightly different in that regard, in that the program. And so that comes down to the library itself. We have library routines for, say, GEM, for example, that is designed to be loaded in our runtime, and other ones that don't. And the session manager makes that decision when it's processing the graph. If it's got enough space, it will actually just pack in a static data flow graph without any of that dynamic reconfiguration. But if it's space constrained, resource constrained, then it will use the time multiplexed ones. However, one thing you can do, in fact, when we tested AlexNet on this, I'm moving the programs in and out, but I'm leaving the data resident. So I can actually leave the feature maps between layers 5 and 6 resident in the memories of the chip and just move the programs in and out.
Okay, great. Thank you. Let's thank the speaker. All right, so the next talk actually has two presenters. Eric Chung, who's a senior researcher at Microsoft Research Next. Eric works at the intersection of machine learning and hardware, and he currently leads the Brainwave project at Microsoft. He received his PhD from CMU in 2011. We also have Jeremy Fowers, who's a senior hardware engineer at Microsoft Research Next, who earned his PhD in EE from the University of Florida in 2014.
Okay, thanks, Ian. I'm super excited here today to tell you about Microsoft's infrastructure for accelerated DNN serving. As you've no doubt heard many times by now, the rise of deep learning has led to significant advances in machine learning. So particularly the use of deep neural networks have contributed to breakthroughs in diverse areas spanning computer vision, speech recognition, natural language processing, and many other areas. So while there's been significant progress in the training and the accuracy of these models, it is still extremely challenging to be able to serve these high-quality models without compromise in online services where you have very tight latency constraints. First is we want to be able to serve these models close to where the big data is, and we want to be able to serve in real time. We want to be able to ingest the search queries, the text, the incoming speech, the sensor data. We want to do it at low cost, low latency, and high throughput. Now, this is further exacerbated by the fact that while we're seeing this growth in size and complexity of the models, this is outpacing the rate of CPU growth. So in response, we've now seen a Cambrian explosion of DNN accelerator technologies, or what I refer to in this talk as DNN processing units. These are domain-specific processors specifically tailored to the needs of deep learning. There are many examples of what I call hard DPUs being developed by large companies, startups, as well as research institutions. Hard DPUs have to commit at design time to a specific set of operators in data types and precision. Soft DPUs built on FPGA technology, on the other hand, don't have that limitation. You can adapt the microarchitecture, the precision, to the needs of the application. While there's been a lot of attention and focus on hard DPUs, and there's been some work on soft DPUs, there have been no widespread examples of soft DPUs being deployed at large scale. So a conventional wisdom that gets floated around is that any type of soft DPU on FPGA must necessarily be less efficient and performant than hard DPUs. And while that's certainly true, if you took exactly the same RTL and you lowered it onto both, you would definitely see a gap. But that's not really the best way to actually harness FPGAs. So we can leverage the flexibility of the FPGA to adapt the microarchitecture exactly to the needs of the application, and in some cases be able to close the gap between soft and hard DPUs, in some cases even be able to exceed the effective performance that you get out of a hard DPU. This is enabled by two things. First, again, as I said, the FPGA, at design time, you don't have to commit to any specific design choices. You can make bold changes without worrying that you might have to take it out later or you didn't put in the right thing from the start. Last thing I want to mention is that at Microsoft, we can actually leverage the fact that we have the world's largest cloud investment in FPGAs, and we can use our technology to run on that scaled infrastructure. This is a bird's eye view of what I call Project Brainwave. It's a scalable FPGA-powered DNN serving platform. I characterize it as being fast, flexible, and friendly. You can take a pre-trained DNN model, and what we do is we lower that down onto a distributed fabric of network-attached FPGAs, where the FPGAs live as first-class citizens on the network. The FPGAs can be pooled together to form what we call a DNN hardware microservice. The heart and soul of the Brainwave technology is the Brainwave soft DPU. It's an adaptive soft processor that's optimized for what I call real-time AI. All of Brainwave can run on a configurable cloud at massive scale. This picture illustrates Microsoft's hyperscale cloud infrastructure. At the outer layer in the squares, you have the CPU compute layer. And at the center of it, you have a converged data center network that binds it all together. And finally, you have a reconfigurable compute layer made up of FPGAs that sits between the CPUs and the network. The FPGAs are actually closer to the network than the CPUs. And you can leverage this infrastructure to do large-scale accelerated DNN serving. Brainwave is deployed in production data centers. What I'm showing you here is the end-to-end serving latency of a fairly complicated model. It's an LSTM-based natural language processing model with tens of millions of parameters that on well-tuned CPU implementations would take you 10, sometimes up to 100 milliseconds to serve, okay, well beyond the requirements of real-time AI latency requirements. Okay? Now, if you only have CPUs in your infrastructure, then you're sort of stuck with a difficult choice. You either can't deploy the model, or you have to scale that model down, in which undesirably giving up accuracy. With Brainwave and FPGAs, we don't have to make that compromise. You can see that in the results here, we can serve this model in under a millisecond at the tail. On average, we're only getting a couple hundred microseconds of latency. And this is essentially invisible to the existing software, end-to-end software pipelines that we're deploying this technology in. And actually, further performance improvements in the hardware wouldn't actually provide us any further gains for this particular model. So for the rest of the talk, I'm going to kind of go underneath the hood of Brainwave and kind of walk you through sort of the major components. Okay, we'll start with the compiler and runtime. The goal of the compiler runtime is to make it very easy and turnkey to take high-level models and be able to lower that down onto a distributed set of FPGAs, or hardware microservices, and soft DPUs. All of that is built on top of an adaptive architecture. It's an adaptive ISA that's completely parameterized, supports narrow precision, it's flexible and extensible to keep up with the fast-changing pace of AI algorithms. As I said, the heart and soul of Brainwave is the Brainwave soft DPU microarchitecture, highly optimized for real-time AI. We've been able to roll out changes in response to changes in AI algorithms on the order of days to weeks. The idea of persistency at scale is really critical to this idea of Brainwave. We're going to get more into the details later, but fundamentally, it is what allows us to achieve that real-time AI for very large-scale models. All of Brainwave runs on top of hardware microservices powered by Intel FPGAs. So we're going to drill into that first. So I'm going to start by talking about Microsoft's accelerated infrastructure powered by FPGAs. This is a single server, okay, that we've deployed into all of our data centers worldwide. Okay, and in there, you have an FPGA that sits in situ, in line between the server's network and the top-of-rack switch. Okay? This organization allows the FPGA to perform both local acceleration and distributed acceleration. Okay? And in the case of distributed acceleration, the FPGAs, as I said, are first-class citizens of the network. They can communicate directly with each other at ultra-low latency, under 2 microseconds per hop on the network, enabling a frictionless way of scaling up large models. This is a picture that shows where the FPGA card is installed in the back of 2 half-U servers. Brainwave fundamentally relies on hardware microservices as an underlying serving architecture. The key idea is this. While FPGAs are physically co-joined at the hip with CPUs, they can be logically disaggregated and formed into independent pools that can be used to map a variety of different services and shared by all of the CPUs in the system. This is very important for 2 reasons. First is that for workloads that don't fit on a single FPGA, you can seamlessly go out to our cloud, grab a bunch of FPGAs, and form a pool out of them. Second is it allows us to actually better balance the needs of software and hardware. What we often find is that hardware acceleration is so fast that if we did a one-to-one pairing between CPU and FPGA, the CPU cannot keep up. So what we can do is actually oversubscribe CPUs to FPGAs, getting better utilization of our data center. Next, I'm going to talk about the compiler runtime and the idea of persistency at scale. The goal of our compiler is to be able to take customer models, so these are pre-trained models developed in CNTK or other frameworks, and be able to seamlessly compile that down onto hardware microservices. Okay, so we take a model checkpoint, we lower that into an intermediate graph-based representation, where we do graph rewriting, we partition that into tasks, we do optimizations, and then we schedule that across a set of different resources, multiple FPGAs and CPUs. Finally, this is all tied together by what we call a federated runtime, which handles the marshalling and the mediating of data as well as the scheduling. Again, as I said, the entire goal of the compiler is to be able to make it frictionless, turnkey deployment of models onto distributed FPGAs without any knowledge of underlying hardware. For the compiler to succeed, it has to do well in at least these 2 classes of problems. So you've heard, no doubt have heard a lot about convolutional neural networks. And so CNNs have been widely studied and evaluated in many architectures. And relatively speaking, actually, CNNs are actually very easy to exploit, right? They have very high compute-to-data ratio. They have many degrees of parallelism. And so that's why I think you see a lot of technologies out there succeeding very well with CNNs. Much less attention has been given towards the class of problems that I have shown on the right, which are these recurrent neural networks based on LSTMs and GRUs. These workloads in particular are much less compute intensive. In fact, they're memory bandwidth limited. Okay? But they are a very important component of many of the state-of-the-art algorithms being used today employing deep learning. So for the rest of the talk, we're going to mainly focus on the class of problems on the right, where it's extremely difficult to get high effective hardware utilization on this class of problem. So a very conventional approach to doing acceleration is what I call local offload and streaming. So you would take all the parameters of your model, and we basically stuff it into DRAM. Okay? And what you do is, when a request arrives to the FPGA, you'll then stream all of the model weights, perform the computation, and send the response back out. And that's great. The unfortunate problem with this approach is that you're massively stranding a ton of capacity, right? And this is particularly true with DNNs, as I mentioned, like RNNs, and LSTMs, and GRUs. You're essentially memory bandwidth limited. Now, a very common tactic to try to improve this to juice this number up, is to actually employ what I call request batching. Okay? So the idea is really simple. All you want to do is amortize the cost of doing that load from DRAM. So rather than servicing one request at a time, you're going to basically queue up multiple requests onto the FPGA, do the streaming once, and then send all the responses back out. And it's a very effective approach. For large batch sizes, you can basically drive up the hardware utilization often to peak performance values. So while this is great, batching does not actually improve the latency of a single request. In fact, it's likely to hurt it, right? Because you've got to wait for multiple requests to arrive before you can service. And this is actually goes against our goal of what I call real-time AI, right? So in real-time AI, I basically want to be up and over to the left, right? I want to be able to serve models at low latency, high hardware utilization, no batching whatsoever. And so, as I said earlier, is that increasing the batch size is ultimately going to be a limit in some of these online services where you have real-time AI requirements. So where does Brainwave lie on the spectrum? It's up and over to the left. We can achieve near peak hardware utilization with no batching whatsoever. So the next couple of slides are going to tell you how we do it. So what we do is we forgo using DRAM altogether. Forget the DRAM. It's too slow. Okay. So we make a couple of observations. If you look at some of these state-of-the-art FPGAs today, you have the order of tens of thousands of distributed SRAMs, or in FPGA parlance, block RAMs, in aggregate providing up to tens of terabytes of memory bandwidth, which is a perfect match for these memory-intensive workloads. We also observe that in these real-time AI services running in the cloud, these models run persistently. Okay. So our solution is to persist all of the model parameters in FPGA on-chip memory during service lifetime. Okay, so what does that actually buy us? So what that buys us is when a request arrives to the FPGA, we can activate all of the resources on the chip to service that single request, okay? And this is no small feat, mind you. It's very difficult to do this. But you can take all of the tens of terabytes of memory bandwidth, every compute resource on the chip, to making that one request go fast, okay? So you might be asking the question, well, what if the model doesn't fit in a single FPGA? I'm hosed, right? So hopefully it should be obvious to you by now why hardware microservices is so important to this technology. When we run out of capacity on a single FPGA, we can span multiple FPGAs. We can pull in actually a data center scale's worth of resources to form these pools of hardware microservices. This allows us to have our cake and eat it too. We can essentially have each FPGA operating at peak efficiency with completely batchless, getting ultra low latencies on models where we don't have to scale down and compromise. In the next couple of slides, I'll give you a few concrete examples of how the compiler can take these large models and map them down onto FPGAs. So this here is a very common motif that you'll find in natural language processing problems. So it's a multi-layer LSTM. And so what I'm showing you on the upper right are a set of equations basically defining what the computational step in each time step of the LSTM for each of these yellow boxes. The bulk of the model parameters are represented by these W and U matrices. So what we could do is essentially split it across an 8 FPGA microservice. So we pin each of the model parameters into each of these LSTM. We take each of the model parameters of each LSTM cell, we pin it on each FPGA. And when the CPU wants to basically process or serve this model, it goes to the head of the pipeline, and the request basically makes its way to the head node, basically goes through the intermediates are forwarded between FPGAs, and then the response is routed back to the originating CPU. So between all the intermediate hops, there's basically no software in the loop. You also might be wondering what the latencies are. Again, the one-way communication is under 2 microseconds a hop. So it's a very low amount of overhead. You might also be wondering, well, OK, doesn't this mean that I've massively over-provisioned 8 FPGAs for one CPU, and I'm going to have a lot of stranded capacity? So with hardware microservices, we don't have that problem because we can take all the CPUs and actually have them share the single microservice. Another style of parallelism we can exploit is what I call intralayer parallelism. So in the previous example, my instantaneous peak throughput devoted to one query is still one FPGA. So if I want to go even further than that, I can actually take individual matrices within a single cell and actually partition that and slice it across multiple FPGAs. So at every single clock cycle, basically all 8 FPGAs here are processing a single query. So I'm going to next turn it over to Jeremy, who's going to tell you a little bit more about the soft DPU microarchitecture.
Thanks, Eric. We designed our DPU to be fully software programmable with specialized instructions for common DNN primitives such as matrix vector multiplication. We then optimized for batch size of 1 and scaled up to next generation Stratix 10 FPGAs from Intel with up to 1 million ALMs. The result is that a single SIMD instruction can invoke over 130,000 floating point operations per cycle. We achieved this scale by designing our own numerical representation that we call Microsoft Floating Point, or MSFP. And MSFP maps very efficiently down onto the FPGA resources. We then apply these resources by applying a variety of techniques, such as matrix tiling with inter-row and intra-row parallelism within the matrix tiles, along with deep pipeline parallelism between the instructions. Finally, because this is a soft DPU built for FPGAs, we're able to add new instructions to it on the order of days or weeks, which means that we can always efficiently evaluate against the latest DNN models. Now let's do a deep dive into the microarchitecture. The largest component of the design is the matrix vector unit, which is shown in the top left corner. The matrix vector unit is composed of these kernels, each of which is responsible for evaluating a tile in a larger matrix vector multiplication. These kernels are dynamically composed together to keep utilization up while also preserving flexibility. The other main computational engine in our DPU is the multifunction unit, 2 of which are shown in the bottom left corner of the diagram. These multifunction units implement a variety of vectorized functions that are common in DNN models, such as sigmoid and Hadamard product. it is pretty easy to introduce a new function to the multifunction unit so that we can stay up to date as the DNN landscape shifts. All of this is tied together by a network on chip that allows us to dynamically compose all of these operators together so that we can map DNN models into deep pipelines in the architecture. This is particularly important for batch size of 1 because it means that we can quickly evaluate individual layers for individual requests. And this is important because the result of one layer is then going to be input into the next layer. Now let's take a deeper look into the kernels, since they perform the majority of the flops. These kernels are made up of an array of hundreds of parallel dot product units. In turn, each of the dot product units are made up of tens of lanes of multipliers and adders. Now, all of these operators require fresh matrix data every single cycle in order to stay busy. That is why every dot product unit has its own dedicated bank of blockgrams. Together, these blockgrams form a massive distributed matrix store that can be read at up to 20 terabytes per second. We drew up this figure to give you an idea of the massive scale of this system. Multipliers and adders from the matrix vector unit cover the vast majority of the FPGA. They're organized into lanes, and then into dot product units, and then into kernels. Here we're showing you 4 kernels, each of which occupies one corner of the FPGA. All right, so that's the architecture at a glance. Now we need to talk about our research into numerical representations, which is critical for achieving high performance for DNNs and hardware. So we recently disclosed in 2015 that we have a large deployment of Stratix 5 FPGAs in our cloud. So let's use those as a baseline for starters. If we implement our Brainwave DPU on the Stratix 5 and configure it for 16-bit integer, which is a traditional format, we get 1.4 tera operations per second on the Stratix 5 FPGA. If we then go down to 8-bit integer, this increases our performance to 2 teraops. Things get more interesting when we switch over to our 9-bit version of Microsoft Floating Point, or MSFP9. There, we're hitting 2.7 teraflops per second on the FPGA. Moving to MSFP 8-bit, we get 4.5 teraflops per second. Now, this is on Stratix 5, which is an FPGA that was introduced in 2011. What happens when we take the latest and greatest Stratix 10 FPGAs from Intel and put the Brainwave DPU on those? We've prepared a demo so that we can show you this today. All right, so our demo application today is going to be a large GRU-based model with a hidden dimension of over 2,000. That means it's 26 times larger than AlexNet and 5 times larger than ResNet 50. As a baseline for this demo, we're going to model a throughput-oriented DNN processing unit, like the ones that Eric was talking about earlier. We're going to say that this device is a contemporary of the Stratix 10 and that it's provisioned with hundreds of gigabytes per second of off-chip memory bandwidth. So I'm going to invoke the demo here. And there's some estimated performance for the throughput DPU. Now, throughput DPUs put their best foot forward at high batch size. However, we are primarily interested in real-time AI, where you can take requests coming in and evaluate them as quickly as possible. You can think of this target as the upper right-hand corner of this graph, where for a single request, you can take all of the available performance from your device so you can evaluate quickly. Now let's simulate what happens if we take our throughput DPU and dial down the batch size. So what you see here is that the memory bandwidth of the throughput DPU cannot keep up hardware utilization. And so as we approach lower batch sizes, which is really our target for real-time AI, the throughput DPU does not come close. It's nowhere near the upper right-hand corner of our graph. All right, so now let's talk about the Brainwave DPU. Right now, I am remoted into a server at Microsoft headquarters, where we're running the Brainwave DPU on a Stratix 10 board. When I hit enter here, we're going to start running our large GRU-based model on the Stratix 10, and the green dots that you see on the graph are going to be live performance data. All right, so there we are at high batch sizes. Now what happens when, again, we dial down the batch size and see if we can hit this real-time AI target in the upper right-hand corner of the graph. All right, there you have it. The Brainwave DPU achieves the same high performance with no batching. OK, so that's what performance looks like. Let's peek into the latency logs that we just generated to see just how fast we're evaluating these requests. So if we peek into the latency log of our simulated throughput DPU, it shows that we're evaluating this large GRU model in about 65 milliseconds. Now, if we look in the Brainwave log, what we're seeing is that we just evaluated a large GRU-based model in under 1 millisecond. The 20 terabytes per second of memory bandwidth that we have on our DPU shines here to give us over 50x latency improvement over the throughput DPU. This is real-time AI. Now let me go back to the slides. OK, running low on time here, so we'll move through the rest of the deck. All right, so that was our demo results. And we actually have quite a lot of headroom available to optimize for Stratix 10. So at 16-bit integer, we're going to hit 12 teraops per second. And moving up to Microsoft floating point 8-bit, we are going to hit 90 teraflops per second on a single Stratix 10 FPGA. Now, you're all probably wondering, what is the effect of MSFP on the accuracy of DNN models? So we put together this graph here, and what you're seeing is we took 3 real neural network models from Microsoft Online Services, and we converted them into MSFP to check out the accuracy difference. So the blue bars are the accuracy of the model in float 32, and you're seeing a normalized value there. And the orange bar is what happens when we convert to MSFP8. And there's just a slight dip in accuracy there, which is why we developed a set of training optimizations that recoup all of that lost accuracy. So to wrap things up, there's just a few extra things I want to leave you with. One is on the left here. You can see how performance is going to be improving for us as we move from previous generation Stratix 5 to Aria 10 to the next generation Stratix 10 parts. On the right, we've got a floor plan from the Quartus tool of putting the Brainwave soft DPU onto the Stratix 10 280 part. What you can see here is that we stretched to fill up the entire design, and we're mapping 4 of our kernels onto this chip. We're also using 100% of the available digital signal processing blocks on this FPGA. Finally, I want to point your attention to the bottom of the slide. With the Stratix 10 280 and Brainwave soft DPU, we are going to be hitting 720 gigaflops per watt of power efficiency. All right. Thank you all for your attention. I'm going to hand it back to Eric now to wrap up.
Thanks, Jeremy. So what you just saw was Brainwave technology running on Microsoft custom hardware powered by state-of-the-art Intel Stratix 10 FPGAs. We think that this is going to be a game changer for Microsoft. It's going to allow us to serve models of unprecedented scale, complexity, and quality at ultra-low latency and high throughput. It's going to enable us to extract more insights from data, enable more intelligence in the cloud, and it's going to also move us towards more human-like machine interaction. So we've been working very hard to make this technology available to external customers, and future announcements will be forthcoming. Thank you.
Right here. Okay, on the right.
Thank you. Nathan Brookwood, Insight 64. Can you give us a little bit more color on the FP8 format in terms of the split between fraction and exponent? And why do you think having such a much more limited floating point representation has such a little impact on the overall accuracy of the model?
So the question is, more detail about the MSFP. So unfortunately, at this time, I'm not able to disclose information on the specifics of how that works. There has been a lot of published work, certainly, at least in the narrow precision domain, showing that neural networks can be quantized down to very low bit widths, even below 8 bits, and still essentially retain all their accuracy. Now, with that being said, we're not actually doing fixed point. It's not integer fixed point, and it's not IEEE floating point.
Thank you.
I have a question about the sort of similar.
Sorry, could you repeat?
So when you had a MSFP, actually the accuracy dropped just a little bit, but after you retrained it, the accuracy actually become even better than the original. So how?
We observed that too.
Yeah.
And actually, that's just, I think, a little bit of noise. What we find is even when we're training the same model over and over, you see fluctuations within 1%. And so I don't think we're actually reading into that anyway, that it's actually fundamentally better than float.
Hello, Dennis Nguyen, Cisco. Maybe you can guess what I'm going to talk about, but do you think that you're at liberty to talk about packet sizes and where your latency constraints probably come from?
Right. So, so we have a protocol. It's called Lightweight Transport Layer. It's an RDMA-like sort of. What it does is it basically takes messages of pretty large size, I mean, almost unbounded, and it basically shards that into, packets. In actual measurements we've done at scale, we see 2 microseconds per hop, but when we look at the entire diameter of the network, we're at about 10 microseconds. So the latency is actually quite good. In terms of networking bandwidth, certainly that can be a concern if you have really large models and you have a lot of auto-all communication. And this is where the hardware microservices and the compiler comes into play, where we have to do more intelligent partitioning and scheduling so that we can keep communication local.
Ha from Intel. 2 short questions, if you don't mind. First one is about persistence and residency in the data center. So I understand that you keep a specific model within the M20Ks of the FPGA. Do you also keep alternate networks on the DRAM? That's how you swap when you switch services? And how often does that happen? And how important is that to the microservices for data center?
Right. So the question was, do we keep other models on the DRAM? I mean, certainly we can essentially swap in and out based on demand, right? So
right,
that's
but is that a critical? How critical is that to you?
It's very scenario dependent. So you have some services that are just running one thing and that needs to run really fast. You have some places where you have diversity of models. So a very common example is that you're trying to flight a new model, right? You're trying to experiment. You want to keep what you've got, but you want to be able to preserve. You want to be able to bring in something new and try that out. So with hardware microservices, we can solve this in a couple of ways. Basically, we leverage scale, right? So you can essentially devote a fraction of your pool to a specific type of model, and then you might have a remaining pool that can be used to bring up new models, right? And then you can sort of swap between them.
So would it be right to take from your answer that in a real deployment scenario, when you're actually serving, that it would be okay for you guys, even if there was no DRAM storing alternate models, because the models are so persistent and the residency time is so high that you could bring it out over the network if you wanted to.
Yeah, so in some deployments today, we completely don't use the DRAM. That's certainly true. While I said that we don't use the DRAM for buffering the weights, you might still want DRAM to be able to buffer incoming network traffic. So that's why we keep the DRAM around.
Okay, so we're actually out of time. Let's thank the speaker.
Thank you.